Okay, so we all got stuck on 51 and I just kind of saw the solution to 51, but that's no way to go through solving calculus problems. There should be a method to the madness. And there is. This one has a really elegant solution and a nice little piece that we missed at the beginning that actually uses the function, well, not function, but the relationship, in order to help solve for x and y. I noticed that this relationship actually looks a lot like some sort of deranged quadratic. So I factored it. And I solved for x, y. And I got two possible solutions. I'm going to use these later when I actually differentiate implicitly to help me plug in and get rid of some values so I can actually combine like terms and solve for x and y. So my original function, remember, was x squared y squared plus xy equals 2. So I'm going to differentiate with respect to x, and I get 2xy squared plus 2x squared y prime plus xy prime plus y equals 0. We all got this far in class. We also decided that since the problem is asking us when the slope of the tangent lines is -1, that we could substitute in for all of our y primes. So doing that, I get 2xy squared minus 2x squared y minus x plus y. I also have some other substitutions I can make. I can plug in for xy. I'm going to start with xy equals 1. So I don't really see the xy, so I'm going to pull it out so you can see it. 2y times xy minus 2x times xy minus x plus y equals 0. So now I can substitute for these xy's. I'm going to do it first with xy equals -1 from above. Here. Whoops, here. So I get negative. Did I say 1 or -1? Hang on, let's check. 1, not -1. So we get a 2y times 1 minus 2x times 1 minus x plus y equals 0. So I substituted xy equals 1, and I get this new expression. I can combine like terms now, and I have 3y's minus 3x's equals 0, which tells me that x, or y, must be equal to x. If y is equal to x and xy equals 1, that means what? Well, I can make a substitution. I'm going to substitute y equals x. I'm going to substitute in for y. And I get x times x equals 1. Well, if x squared equals 1, that means that x either equals 1 or x equals -1. Since x equals y, when x equals 1, y equals 1. Since x equals y, when x is -1, y is -1. So we have 2 points already that work for this. 1, 1, and -1, -1. We need to double check and see if this part of the solution to my quadratic, the original equation, also works. So I need to see if xy equals -2 also works in my derivative, my implicitly differentiated function, which was 2xy squared plus 2x squared y prime plus xy prime plus y. Okay. So keep in mind y prime should equal -1, so I'm going to put that in here first, just like we did before. 2xy squared, whoops, minus 2x squared y minus x plus y. Nothing new so far. Here's where I'm going to make my substitution for xy, just like I did before. So I have a 2y times -2 minus a 2x times -2 minus x plus y equals 0. Simplifying out a little bit, -4y plus 4x minus x plus y equals 0. Again, I have an expression where I can combine my like terms. -3y plus 3x equals 0. So that means that 3y equals 3x, y equals x. Again, I do need these two things to be true at the same time. So if I make a substitution, I get x squared equals negative 2. Ah! That's not possible. There's no squared number that equals a negative number. Okay, what if I substitute in for x instead of y? Then I get y squared equals negative 2. Again, we can't have that. So xy equaling negative 2 doesn't work for us. So my only solutions for our original equation, having a tangent line with a slope of negative 1, are at the points 1, 1, and negative 1, negative 1. Fancy, huh? I thought it was pretty cool. That little piece at the beginning, solving not for x, not for y, but actually solving for the product xy, really helped. Hope you enjoyed the proof. Have a lovely long weekend.